Hi everyone, welcome back to Math 256. This is Scott. Let's get started. Now we're going to be talking about section 2.4, where we're going to do our first in a couple of treatments of different methods of numerical approximation of solutions. This is section 2.4, numerical approximations, Euler's method. So this is Euler's method, which is the first and sort of the most bare bones method of an approximate solution to a differential equation. So here's the setup. We are given a first order ordinary differential equation. So that's going to be something along the lines of dy dx is equal to f of x and y. So we have a differential equation as a function of both x and y, but it's only first order. Now, we are also going to take as a given we're going to take as given a specific initial condition, which is going to be y of x naught equals y naught, and step size h. Alright, so this is our setup. Now let's just think about this. Think about how this would have to work. So here's the here's the graphical interpretation of what we're about to work out. So graphically, we can take the slope field for the differential equation, and let's just say what we have is something where it's getting shallower. Over here, maybe it's going slightly less shallower, and then something more or less like that, I don't know, and then maybe something like so. So we have some slope field, and let's say down here something else. Okay, so take the slope field for the differential equation. I just drew one. Then plot the initial condition. And let's say that that initial condition was like right here. Then the use of the step size here is that's going to tell us how far out to step in the x direction before we reassess and figure out a new little line segment. Then draw a line segment with a horizontal run, so as in like rise over run, the horizontal run h. and slope determined by the differential equation. And then once you have reached that point, from there, repeat. By drawing another line segment in the same fashion. Continue. So basically, from some initial condition right here, we would just use the slope field to go out some amount, and then maybe we would draw a new one, going out some amount, and then some new one, going out some amount. And what we'd have here is basically the differential equation's equivalent of what we would do, although in a more discrete fashion, if you were to actually just do like you did on the first problem set and sketch a solution to a differential equation. So then this is an approximation of solution. A solution curve. Curve via line segment. Now let's think about what this would mean actually numerically. So these approximation methods are always, in fact, although they may have a geometrical or a graphical motivation behind them, they're always actually implemented numerically, and that's almost always through the use of technology. So numerically, let's have a look at how this would play out. So let's take, so we start with x naught and y naught. Now, as for the new x values, those are always going to happen by marching along according to the step size. So xi plus 1, I guess, is equal to the previous x plus h. Now, as for yi plus 1, the way that works is, let's just think about it here, we've got a slope, we've got a previous y value, and we've got a slope which is given by the differential equation, and we step out h, and how far do we rise? Well, that's going to be equal to f of the previous one, which I should say, I'll just say mi, where, so this is equal to the previous one plus mi times h, where mi is equal to f of x I y I. So that's, after all, what the differential equation is giving you is the slope, and so then that gives you that the next y value is going to be y I plus 1 is going to be whatever the previous I value was, plus plug in the previous x value, the previous y value into the differential equation, into the formula for that. That'll give you the slope times h. Now this is something that we can actually do more or less by hand, although as we start making the step size smaller, then it becomes more and more laborious to do it by hand calculations. But we can also use technology for this. So smaller step size implies more accurate. Approximation. But the smaller step size also means more calculation necessary. So let's just try an example of this with a relatively simple case like y prime is equal to x plus y, and an h which is equal to 0.1, and an initial condition of y0 equals 1. Now this is linear, and you could actually figure out the exact solution. So solving exactly. Solving exactly. And you do that with an integrating factor. Gives, just for the record, y equals 2e to the x minus 1. But we are now going to be thinking of this as though we couldn't even actually have done it exactly. But we'll just try to put ourselves in the perspective or in the shoes of a technological device producing an approximate solution. Now, although the numerical side of things is something that we will be primarily on the consumer side of, it's going to be a thing that's generated by technology. Still, it's good for us to at least go through the motions of seeing what this is like deep in the guts of the machines that are doing our dirty work for us. So here is a table of approximate values. So here are some of the important pieces of the table here. So there is going to be I, which is going to be the index of which step we're actually on. So we're going to start with the initial condition, which is step 0, then 1, 2, 3, and say 4. And then what we'll have are the x values that will be going up by these step sizes. So from an initial x value of 0, because our initial condition was y of 0 equals 1. So for an initial x value of 0, they're going to be incrementing each time by the step size of h. It's going to be 0.1, 0.2, 0.3, and then 0.4. Now, as for the y values, we currently know the first y value, but then to get any further y values, we actually need then to use the actual f of x, which is part of our differential equation, to tell us the slope, which is going to indicate what the next y value is going to be. So f of x1 or xi yi is going to equal, according to our differential equation, xi plus yi in this particular case. And this was, remember, y prime, which equals x plus y. So here we're going to have 0 plus 1 is equal to 1. And then this part over here is going to come from 1 times the step value plus the previous value. So that's going to be 1 plus 1 times 0.1, which is going to be 1.1. And then we use that to get the next f value, which is going to be this plus this, which is going to be 1.2. And then we use this plus the previous y value to get the next y value. So it's going to be 1.1 plus 0.1 times this, which is going to be 1 point, and then it's going to be, so 0.1 times that is going to be 0.12, so it's going to be 1.22. And then here we're going to add those together, so that's going to be 1.42. And then we're going to in turn use this to get the next y value. So from a y value of 1.22, we step 0.1 at the rate of 1.42, so it's going to be plus 0.142. So it's going to be 1.3 and then 6.2. And then you add those, and it's going to be 1.662. And then finally, we'll be at the last one here, which is going to be 1.362 plus, and then it's going to be 0.1 times that. So that's going to be here. So this also will make a good commentary here. This will be 1.362 plus 0.1 times 1.662, which, according to my calculations, is equal to plus 0.1 times 1.662 is equal to 1.5282. And if that's where the table ends, then that's all we need. So that gives you that. That gives you that. And that's how the tables would fill out. Now let's have a look at how to do this technologically. So one thing you could do is you could actually just make the same table in the same way, but actually execute the grunt work technologically. Or alternatively, what you can do is you can actually, and if you're using a TI-89 for example, you can actually go ahead and use your calculator's built-in options for differential equations. So here, if you recall, there is in the mode setting, there's in the mode setting the option of graphs via differential equations. And if you go to the diamond and y equals screen, you can here put in whatever you like for your differential equation. Now x and y have become t and y1, and you can put in your initial condition, which is going to be, according to this one, y of 0 equals 1. And now in the tools screen, if you go to the formatting stage, you can make certain you can make certain changes. For example, solution method. Instead of the RK method, you can make it the Euler method. And then press enter. And then here in the window section, what we can actually do, and then in the window you can adjust the step size by changing the t step to point 1. So whatever it was already, maybe it was 0.2, make it 0.1. And you can set what the t naught is equal to right there. And then if you want to look at a table of values, you can go to Diamond Table Set, and that gives you the chance to adjust the setup of the table. And here, what we can do, let me see if I can adjust the glare. So you can put the table start of 0, or whatever your initial condition is, and then the change in table you can make 0.1 as well. And then here you can make the independent variable in your table either automatically generated or generated as you ask for it. I'm going to put it as auto, and then I'm going to press enter, and then I'm going to actually go to the table, and you'll notice that it automatically generates the y values that go with these x values according to Euler's method with the given step size. And you'll notice that it matches what we generated by hand in this table. Now, one of the big advantages to this, if you go back to the setup, is that you don't need to necessarily put all of the intermediate values in here. So you can make your table go up by ones, and then that suppresses all of the intermediate values if you are only interested in some direct values later on. Also, you can if you go back to setup, if you make this ask instead of auto, then what that does is it gives you the option of now deciding what new t values you want to put in there. Like maybe I want to put in not 5 but 10, and then it'll generate the y value that goes with that. So this is how you can get your calculator to generate for you the values according to Euler's method at a given step size. So the step size, once again, you change in the t step in the window section, and then you can adjust the starting value at the different pieces. There are also a lot of ways you can do this with various things on a computer, particularly if you don't have a TI-89. A TI-89 is actually a pretty convenient system for doing these sorts of calculations. However, if you don't have a TI-89 calculator, here's what you can do on the internet. Alright, now let's look at a couple options for other technological ways of generating the approximate solutions. So one way, if you have a TI-89, is to use that. If you don't have a TI-89, then one thing you can do is the same slope field generator that we used earlier to sketch solutions using slope fields. If you scroll down to the one from Bluffton, that was the one that I gave my endorsement to before, and I give it to this one again. And here, actually, if you see, we have a 1 ODE. We can put in just the same differential equation that we were talking about already. I'm going to change these values a little bit. I'm going to change an x value, minimum 0, maximum 4 is probably good. Y value, I'm going to start with 0, and I'm going to go up to, I don't know, 50. Now here you have an option for different solution methods, and you have Euler, you have improved Euler, which we'll see in the next section. You have midpoint, Runge-Kutta, and another Runge-Kutta. And then over here, this gives you the option for the step size and then the initial condition. So I'm going to put in the initial condition of 0, 1, and then that gives me a solution curve here. And then if I want the actual y values of the points along that solution curve, I can actually click down here at the numerical solution tables, and what you see here is the x values, the y values, and then the delta y's, which actually are the same thing as the slope times the h. So this is very similar to the f of xi, comma yi column that we had before. The difference is it has been multiplied by the h. So then you can scroll down and you can see a bunch of the values here up to the one that was indicated by us as our maximum y value or x value here. And that's how you can do that. Another option for doing this that doesn't involve the internet necessarily, but any kind of spreadsheet software, would be the following that you can do in Excel. Because Euler's method is so easy to implement, you can actually do this without even necessarily saving any kind of template or anything like that. You can actually just put in the columns that we just did by hand, and it'll be very straightforward to actually just put in pretty much the exact same procedure we did on pen and paper, but this time just using the abilities of the spreadsheet software to fill in all the blanks based on the previous. So you can just do something like this in order to get the step column going. Just put in enough so that it can continue the pattern, go down a ways, and now for the x values. For the x values, you can actually just take something like the x initial value here, which equals 0. And not that it's necessary in this case, but just in general, if you wanted to, what you could do here would actually be, I guess right up here would be fine too. You could actually do plus 0.1, which is the h, times the step size, and that would give you a formulaic way of generating all the x values. Again, not necessary here, but sometimes it might be a little bit less straightforward. Now, as for the y values, what we can do is we can actually go ahead and put in the first y value, which is just 1. And now, what we're going to do for the succeeding y values is we'll make a formula for it, and it'll be equal to the previous y value plus the step size, which is 0.1, times this entry over here, which we haven't started filling in yet. But that will be where we'll put in the formula for the actual differential equation, and then you can again just pull that down and get those values there, and there they are. And for this, what we would just do is put in the actual differential equation here, which would be the xi plus the yi. So we can just literally do that. Oops. That was me trying to press enter. And then that gives you that. And then as you scroll down that will bring the y's up to speed here. And notice that as of the 0.4, the y values are all in agreement with what we had on our little table. And then after that, they just continue on the way they want to continue until you get these other values. And then one other option that is available to you when you have Excel, if you actually have, through some analytic means, developed the actual solution formula for the differential equation, you can actually put those values in to compare with those y's. So here we could have, for example, exact solution. And we already were able to figure this out. Well, I told you what it was because it was a linear differential equation, so we could have solved it. And so now what we can do is actually get the exact solution as a function of the x column there. So it's equal to 2 times, it's going to be e to the x, and you can do exp in Excel. And then you put in the x column. And then the solution was so 2 times e to the x minus x. So minus x minus 1. And that gives you the exact solutions that we can compare with the y's. So if you look at first, it exactly corresponds, and that makes sense because as of there, we're just at the initial condition. Now this one compared with the y, it's quite close. This one also quite close. Getting a little further away, a little further, a little further, a little further. You'll notice that what's happening here is that at each step, the y values of the exact solutions are getting a little further and further and further ahead of the y values from the so these ones are here, are the y values from the Euler's method. And what this shows you is that actually the errors in Euler's method will continue to compound on each other. If you use Euler's method and it gets you slightly off, all your subsequent results are going to get further and further off based on that first erroneous value. So let's now return to the notes and make further observations along those lines. Alright, back to the notes. So here is a note about error. Errors in numerical methods, such as Euler's method, will accumulate. In particular, you will have a small local error associated with each step, but then there'll be a cumulative error, which represents not only whatever new mistake is introduced, but whatever previous mistake was already baked in. So there are local errors. These are errors at each step. And then cumulative errors. Then there's cumulative error, which is the total result of previous steps errors. And with Euler's method, it's not a very sophisticated method. So with this particular method, the errors will be more than in any of the other methods that you will see. So when given the option of different methods, if your premium is on accuracy, then Euler's method is actually going to be the one you should shy away from. It's theoretically the most straightforward one, and so it's the one that's easiest to implement, and it's the one that requires the fewest amount of calculations. But it will accumulate errors faster than any of the other methods that we're going to talk about. Alright, so that's all for section 2.4. Join me next time for section 2.5, where we'll discuss an improvement on Euler's method.